Hi, it's Miss Marsden, and what I'm going to do today is I'm going to take you through a revision session on the Earth's atmosphere topic, which we've been covering for the last couple of weeks. Today's first task is the first page in your booklet, which is a revision quiz. What I would like you to do is I'd like you to answer as many of the questions as you can without looking at any of your notes, without looking at any extra information, because what we're going to do is we're going to go through a quick review of the full topic and you can improve them as we go along. So pause the video for as long as you need to be able to answer the questions to the best of your ability for now. And don't worry if you don't remember any of them, because like I said, we're going to go through the rest of the answers throughout this lesson. So what I'd like you to do is grab a different coloured pen, because you can add to your answers. You might want to be improving them as we go along. You might have noticed that when I go through some information that you might have got an answer wrong, and that's absolutely fine. So what you can do is you can correct it in a different colour so you can see your improvements as we go along. So starting at the beginning, on the first lesson where we talked about the Earth's atmosphere and we compared the modern atmosphere to what it used to be like, this is a diagram showing the current composition of the Earth's atmosphere. So you can see it's majority nitrogen at 78%. Then we've got 21% oxygen, and the rest of it is made up from argon, carbon dioxide and water vapour. Carbon dioxide is usually about 0.038% of the Earth's atmosphere, so it is really small percentage. So that's the modern Earth, but how has that changed compared to when the Earth was first formed? The early Earth, like we know, had a molten surface and there was a lot of volcanic eruptions as well. The atmosphere was made up of ammonia, which is toxic, methane and majority carbon dioxide. So if we had to compare that to anything, we'd compare it to the atmosphere of Mars and Venus at present. It's taken millions and billions of years for the atmosphere to change so that life has been able to evolve. I'm going to quickly go through the processes that have led to this, but like I said, we've been through this in previous lessons, so if you are confident with this and you understand it already, just fast forward straight past it. You don't need to listen to it if you already know it. So the Earth's early atmosphere didn't have a solid surface, it was molten rock, and it was majority carbon dioxide, methane and ammonia like the diagram shows. So that was because of constant volcanic eruptions. They also released water vapour and nitrogen into the air as well. So how did that begin to change? So the Earth's cooled over millions of years, and that's because of less volcanic eruptions effectively. The cooling of the Earth allowed the surface to solidify from molten rock to be solid. And when the temperature eventually came down enough, so it fell below 100 degrees Celsius, that allowed the water vapour in the atmosphere to condense, and that fell as rain. It rained for a long time, and what that did is it created oceans, rivers and streams as we know them now. So the Earth's cooled down. That's allowed our oceans to form, and that's what we know as a turning point in the Earth's history, because it gave a place for the carbon dioxide to go and for the levels of carbon dioxide in the atmosphere to gradually decrease. That's because it dissolved into the oceans. And some of that carbon dioxide that had dissolved in the oceans reacted with minerals to make rocks like limestone on the seabed. So that removed more carbon dioxide because it's been locked up into limestone. We're still talking a long way in the past at this point. We're talking nearly 3 billion years ago. This is when the first life was able to evolve, because the Earth had cooled down enough. We've now got water, we've got less carbon dioxide in the air. We're not talking life as we know it now, we're talking simple single-celled organisms like bacteria. So the bacteria could photosynthesize, and algae, which is a very simple organism as well, began to remove more carbon dioxide through the process of photosynthesis, and that gradually released oxygen. So the carbon dioxide levels kept coming down because of the photosynthesis, and that's why the oxygen levels began to increase. So the more oxygen there was, that allowed plants to evolve over time, because plants do need oxygen for respiration as well, like we do. As oxygen levels rose in the atmosphere, that allowed animals to evolve over time. We're talking a really gradual process here. It's not an overnight 1 million years sort of change. We're talking over billions of years here. So the early plants that we discussed earlier have been used to form fossil fuels. So that's been another way of locking carbon up from the atmosphere. And we know that fossil fuels form when they die. They get covered with layers of sediment, which is mud, and they rot, and it gets buried deeper and deeper over time, just like the diagram shows you. If you want to make notes at any point during this video, please feel free to, if it will help you answer the questions. The key point, it's the Earth's cooling and solidifying, which allowed these changes to happen. The nitrogen, which we know makes up the majority of the atmosphere, was released by volcanoes. The water vapour in the atmosphere has gone down to such a small percentage now because it condensed to form oceans. And the carbon dioxide decreased because it has been locked up in rocks. And then fossil fuels from plants, which had taken the carbon dioxide up in photosynthesis. That photosynthesis is responsible for the increase in oxygen in the environment. And that increase in oxygen allowed life to evolve further. So if you need to pause it now to improve your answers to the questions on the quiz, please feel free to. And we're going to move on to the greenhouse effect. I'm going to whiz through this really quickly, because if you need to go into this in more detail, you feel like you still don't understand it, just have a look back at either your notes or rewatch the lessons from previous weeks to help that. So the greenhouse layer is a layer of gases around the atmosphere. It would exist even if humans weren't there, and it's needed to maintain the temperature of the Earth's surface. So don't think always that the greenhouse layer is a bad thing. It's not. It's made up of carbon dioxide, methane, and water vapour, so they are known as greenhouse gases. In terms of the greenhouse effect, you can see this probably just by putting together the information from the diagram, but I'm going to quickly whiz through it. So we've got the shortwave infrared radiation being emitted, so given out by the sun. So that goes towards the Earth. It then is reflected off the Earth's surface, and it passes through the atmosphere to get there. Some of the energy is absorbed, so it increases the temperature of the surface of the Earth. Some of it's reflected by the Earth. If you notice on the diagram, it's not shortwave radiation anymore. Those waves are much further apart, so it's known as long wave radiation. The difference between short and long wave radiation is that the long wave radiation gets trapped by the layer of greenhouse gases, and you can see that it reflects off the greenhouse layer back towards the surface of the Earth because it's trapped. And what that does is that heats up the temperature of the Earth, which is what we know as the greenhouse effect. The greenhouse effect happens anyway because, like I said, that layer of gases will always be there, and it's really important to regulate the temperature of the Earth. But as you can notice from the diagram, the human activity such as burning fossil fuels is having an impact on the greenhouse effect, and it's causing it to become more of an issue. And that's because, as you can see, the greenhouse layer is thicker because of the increased carbon dioxide and the increased levels of methane. That means more of the radiation gets trapped, and that means the Earth is heating up. And that's what we know as climate change. So why are greenhouse gases levels rising? Start off with carbon dioxide, deforestation, and burning fossil fuels are the main problems. You can read that for yourself. Why are levels of methane rising? It's basically more rubbish at landfill site, more rice fields, and more cattle. Obviously, the more humans there are, because the population sizes are increasing, the more food we need, and the more rubbish we're making, which is causing more methane to be released into the environment. So over time, if we look at the scale between 1850 and 2000, that has caused a gradual increase in the temperature of the Earth. It's not been a linear increase, basically it's not been a nice straight line, it does fluctuate, but over time you can see that it has been a gradual increase, even though it has gone up and down. So we can say that the increase in concentration in carbon dioxide, which has gone up over time, can be linked to the increase in temperature change, which we can see in red. And what are the consequences of it? You can make a list from this diagram, just how you did in the previous lesson, but I'm just going to name a couple which I pick out, and that's the infrequent weather patterns, so unpredictable weather patterns, droughts, flooding, higher temperatures. And what flooding and droughts can do, and melting of ice caps, is it can have an impact on the sea levels. And if sea levels rise, if you live near a coast, that's an issue. But also the seas are becoming warmer, and that has an impact on the marine life which lives there. That might be corals, or it might be organisms like whales which migrate, and that has an impact on them as well. You can look into that if you wish, it's not on the specification. So that links us to our idea of a carbon footprint. There's our definition of a carbon footprint, but it's not just talking about carbon dioxide, remember, it's talking about all greenhouse gases. And we talk about the full life cycle of a product, event, or a service, so it's not just as simple as you drove a car. You need to think about, where's that fuel from? Has that fuel been transported before you've used it, for example? So you need to think about how it's made, how it's disposed of, what it's used for in its lifetime. You can do a couple of examples of your own if you want, like we did on the lesson. You can talk about going to a restaurant, ordering a pizza, going on holiday, for example. How can you reduce your carbon footprint? It's just small changes like we talked about, but in terms of making those small changes, it can sometimes be difficult to get people to act on them, because if you, for example, ask someone to eat less meat, they might argue against that. They might say, well, I don't want to be a vegetarian, obviously. So it isn't as simple as just telling someone to do something because they might not do it. So we've talked about our greenhouse gases, so carbon dioxide, methane and water vapour, but there's other polluting gases as well that you need to know about. So they are carbon monoxide, particulates, sulfur dioxide and nitrogen oxides. So what I'd like you to do, I'd like you to pause the video and I'd like you to tell me for each one of the polluting gases I just talked about, tell me how is it produced and the problems it causes. Carbon dioxide's already done for you as an example, and we're going to mark these in however long you need to pause the video for. Please do this on a piece of paper, just on a blank Word document. You don't need to actually complete the table. Carbon monoxide is made in incomplete combustion. If you remember, that is when there's not enough oxygen. And the problems it causes is it's poisonous because it prevents oxygen being picked up by your red blood cells. So effectively you can't get enough oxygen and your cells can't respire and they die. Soot's also from incomplete combustion. And the problems are global dimming and lung disease. Sulfur dioxide's produced when sulfur in fuels like petrol traditionally reacts with oxygen in the air to form sulfur dioxide. That dissolves into the clouds and forms acid rain. Nitrogen oxides are also linked to acid rain, but it's caused by the nitrogen in the air reacting with oxygen in hot engines. So it's not the fuel itself, it's the heat of the engine. So what I'd like you to do, if you haven't been doing this already, is use the information that you've gained from me going through the previous few slides to improve your answers on the revision quiz. I'm going to go through the answers on the next slide, so if there's any you don't know, then please wait for the mark scheme on the next slide. So different coloured pen. Please mark the answers that you've got. I've gone through pretty much all of these apart from the word equation here for photosynthesis on number 5. Please bear in mind that these numbers should be subscript and you wouldn't actually get the mark if it was like this. I should have corrected it earlier. It's me being completely lazy. So it should look like, for example, 602, like that. Next ones. So number 12 is a revision question from the bonding topic. So when you're talking about simple molecules, they'll have a low melting or boiling point, and that's because covalent bonds within them are really weak. So if something's weak, it doesn't take a lot of energy to break them. If you didn't get that one, I'd set yourself some quizzes on Educake about chemistry topic 2, which is bonding. So we're going to move on to the next task, and it's a grid helping you improve both your subject knowledge and the language that you're going to use to be successful when answering questions. So what you need to do is you need to spot the errors and you need to correct them in the box on the right. So I've done an example for you. It says where oceans form. Start that again. So the oceans were formed when water in the atmosphere condensed to form rain. So I've highlighted where the issue is because it just says water. So I've changed that to water vapour. And I've also improved that by saying cooled and condensed. So can you see how I've rewritten it to include the correct specific scientific language? There's then a fluency test at the back of the booklet which I want you to have a go at. And I know the data ones are quite difficult, so what I've done for the calculations, I've put how you calculate them. So for example, to calculate uncertainty, you do range divided by 2. So your range is the difference between the biggest value and the smallest value. So you divide that by 2. So have a go. I'm going to go through the answers to each one. Pause it for as long as you need to do both tasks, please. So we went through the first one together. Second one, the greenhouse effect is when light waves from the sun get trapped in the Earth's atmosphere. That's too vague. So what we need to do, we need to talk about light in terms of short wave radiation and long wave radiation. So please correct that. So for the third one, that's not necessarily that it's wrong, it's just that you need to be really specific with the language you use. You need to talk about evidence and whether we have evidence or not. Fourth one is just incorrect knowledge, so we don't talk about the ozone layer, it's the greenhouse layer. Bottom one's just about being really specific, so you need to talk about the impact of wildfires on animal habitats, not just the environment. So improve those if you need to, please. So incomplete combustion happens when there is not enough air for the fuel to burn. It's not just the air, because we know the air is made up of nitrogen, and that's pointless when we're talking about combustion. We need to talk about oxygen. I pointed out earlier the importance of using subscripts when you're talking about CO2 and H2O, for example. Don't have them floating. They need to be below the line like this. So for the bottom one, here's our equation for how acid rain's formed. It's not a sulfate that's formed, so we have a sulfur and two oxygens, and that forms sulfur dioxide. Here's our answers for the fluency test. For the first one, calculating the value for x. The working out is shown there. So the optimum pH for number 2, you're looking at the quickest. So whichever one's quickest, it's anywhere between 6 and 8. And how could we pinpoint it more accurately and not just say between 6 and 8? We need to do more specific intervals, so closer together intervals like my examples there. So make sure that if you say you need to do more intervals, then give specific examples just like I have. So when you're looking at percentage decrease, so we're only looking at the 3 molar, so 3 molar, which is here. So we only need these values. We don't need any of the other ones. So what you do is you need to find the change. So what is the change? I do 2.6, take away 2.1, and that gives me 0.5. What I then do is divide it by the original, which was 2.6, and that'll give me 0.19, and then I times that by 100 to give me 19%. Uncertainty, like I said, is range over 2. So the difference between the biggest and the smallest divided by 2 will give you 0.045 seconds. Only other one I'm going to focus on is describing the pattern. So all you need to do is relate the distance to the number of bubbles. So as the distance increases, the number of bubbles decreases. So you're only describing the pattern. So all you need to say is the closer the light, for example, 10 centimeters, there will be more bubbles produced, so the faster rate of photosynthesis. Then all you need to do is give a specific example. For example, at 10 centimeters, the number of bubbles is 21. This decreases the further away the light gets. For example, at 50 centimeters, the number of bubbles produced is 8. There are some extension questions at the end of the booklet if you want to have a go at them. Please remember to send your work to your teachers, please, and remember to complete the Educate quiz by Monday at 8 AM.